Try it again. Here we go. So, here's our situation. We've got a ground fault that opens at a certain time, and then the scientists start measuring at a certain point on the fault the width in centimeters over several months. And this is showing up to 9 months. Okay? And we said when you see a graph, usually you're presented a graph that looks like this. But the way we want to think of that is that x is increasing. And as x increases, at any given point in time, that fault has a width. And so as x increases, this is tracking the width of the fault dynamically, right? So that's how we want to imagine a graph when you see a graph or a curve, okay? All right, so here's a couple questions for you to just review the basics of the situation, kind of intro, a couple intro questions. So take a minute, talk to the person next to you. Actually, just question one. Just question one. Okay, is it accumulation or rate of change? Accumulation. That's an accumulation. Accumulation of width, this thing we're measuring. 1.5, 2.225 is right about there where I have the arrow. What does that point represent on the graph? You should have said 1.5 months after the fault opens, they measured that the width was, or they approximated the width to be 5.225 centimeters in width. Okay, that's what that point means. And the whole graph is just a whole bunch of points, like that one, that you just interpreted. Okay? So now, by observing this graph of accumulation, describe in general what the fault width is doing. Okay, so holding constant, is it increasing or decreasing? And if it's increasing or decreasing, how is it increasing or decreasing? Slowly, moderately, or quickly? So, for instance, at 0.25 months right here, what would you say? Would you say it's holding constant, increasing, decreasing, and how? If so, how? Increasing. Okay, increasing. Slowly, moderately, or quickly? It's increasing quickly. It's increasing quickly. So I want you to do that the same thing for these other x values, 1, 2, 3, 4.1, 6, and 8. Just in general, based on the accumulation graph, what could you say about what the fault width is doing at that moment in time? Go. Okay, so your answers may vary a little bit. It's about the idea, okay? It's about the idea. Here's how I interpreted it, so you can check. So check and see if this is what you said. Go. What do you think? Is that pretty much what you said? Does that make sense? Okay. So we'll just hold on to that. So, here's some more questions. What does the rate of change value mean in this context? How do we estimate rates of change values last class? And estimate the rate of change at the new values of x in the table, what are our new values here? I think they are 2, 4.1, and 8. So the ones I underlined in red there are new values. I think we did 0.25, 1, 3, and 6 last time. So I added some new values. So go, talk for a couple minutes, answer these 3 questions, 3, 4, and 5. Or 3 and 4. Just 3 and 4, and then we'll do 5 together, okay? So 3 and 4. Okay, so let's review. So here is at x equals 1 month. X equals 1 month, just as a review. And what did we said that the width of each of these squares in the grid was 1/4 of a month, and the height of each square was 1/2 centimeter. And so we used the grid based on 1/4 month. The squares were 1/4 month wide by 1/2 centimeter tall to estimate. And we said this one was pretty straightforward, that if we looked at a change of x of 1/4 of a month, we estimated that the change in width was about 1/2 centimeter. It's like in one of these squares, it's one full side of the square on the width and one full side of the square on the height. So that was, and so to calculate the rate of change, we take delta y divided by delta x, or the size of the change in y relative to the change in x, which would be 0.5 divided by 0.25, and we got an estimate of the rate of change was 2. What are the units on that? 2 what? Centimeters per month. 2 centimeters per month. Okay, and so here were the values that we got. For doing that same process at 0.25, we got 4 centimeters per month, and then at 1 we got 2, at 3 we got negative 1.3, 6 we got 2. So let's look at these other 3. Let's go in here at 2. So for a change in x of change in x of 0.25, how much does y change? Tiny, tiny bit, right? Okay. And if we took a smaller change in x, let's just take a change in x of about, say, like 1/4 square. How much does y change? Like 0, it doesn't change. So if we're just estimating, Is saying that the change in y is 0 there relative to the change in x, is that a fair estimate? Yeah, this is fair. If we just look at a small enough change in x, we could estimate that the change in y is 0 for that change in x. Is that okay? Everyone okay with that? All right, so we can put in, and we're just estimating, so we'll put 0 in here. Okay, 4.1. There we go, 4.1, right about here. What about a 4.1? For a change in x, how much does y change? Staying constant, so it's no change. So 0 over whatever change in x we pick. So we pick, you know, like 1/10 of a month. We get a change in y of 0 centimeters. 0 divided by 0.1 is 0. So let's do 8, which won't be 0. There we are. Okay, so let's do 8. Well, I'll let you do 8. 8 is right here. Am I in the right spot? Yes. Here we go. Okay? You do 8. Go. So this is for x equals 8. Estimate the rate of change. Estimate the rate of change. Okay, so there's different ways to look at it. So I looked at a change of x of 0.25 again, so one full square side length here, and so then if this from here to here is 0.5, from there to there is 0.5 centimeter change, then what fraction of it would be from there to there? Does that make sense? Like, so how far of the way up are you going from here to here to get to right there? It looks to me like about a quarter. About a quarter of the height of one square. So about a quarter of 0.5 centimeters. So then we're going to take delta y, is that 0.125? Divided by 0.25. You may be slightly different, but you should be in the ballpark. Which is 0.5. What are the units? Centimeters per month. Centimeters per month. So you may have used different numbers, but did you get something close to 0.5 centimeters per month? Then you're fine. If you look this way, where are we? If you look this way, you might choose a half or a third, right? So if your delta x was this, and that's your delta y, that might be a half or a third of 0.5, and you may have something slightly different. Okay. So what did I say? 0.5? Okay. Cool. So, what does a rate of change function mean in this context? What does the table have to do with it? Go, talk. What does a rate of change function mean? What does the table have to do with it? Go. Let's start with part two. What does the table have to do with it? What does the table have to do with a rate of change function in this context? Does it have anything to do with it?
If you were to have a rate of change function, and you plug in any x, so 3 will give you negative 1.3.
Okay. All right. So you're saying that the time in months is input, rate of change is? The table is the rate of change function, or it is a representation of it. Okay, it is. So that this is the input would be our x quantity, in this case time since the fault originated, and the output is the rate of change. So it's a whole profile of rates of change. For any given time, the rate of change function tells you what the rate of change is at that time. Okay, so how do the output values of the rate function represent this, what we found in the second column, what the fault is doing? How do the output values of the rate of change function represent what the fault is doing? So compare those numbers to what we wrote in the second column, and what's the connection? What is the connection between those numbers and column 2? Go. So you should have talked about or discovered that the rate function is just a numerical version of this, what the width is doing, how it's changing. It's just a numerical version of that, right? So if we're increasing quickly, the rate of change is positive or negative? Positive, and what kind of value is it? Bigger, right? And if it's increasing moderately, positive or negative? Positive, but not such a large number. Okay, holding constant, rate of change is 0. Decreasing, rate of change is negative. And the value of that negative is how fast it's decreasing. Okay, increasing slowly. Right, so we pick that off looking at the graph, and we get this number that tells us that every month we estimated that it's going to open up just 0.5 centimeter per month at that point. Okay, so here is the width function, the accumulation function. 2 times, I think I didn't have the 2 there last time. There should have been a 2 there last time. This is the right width function. What does the mastery exam have to do with this whole discussion? What does the mastery exam and say that W function have to do with this whole discussion? Go.
It just lets you migrate to the point of most which is most, it's more, I guess, reality, showing us a simple function of to draw something in the world, changing something that
full volunteers here. So what? So here's just like we've done the mastery exam, right? You learn these rules for finding the derivative, right? So I follow the rules: 2 times rate of change of the exterior function with respect to the interior. So this is just the same thing down here in the square root. Same thing as this. Times the derivative of the inside part, right? Did I do it right? Am I master? Did I pass the mastery exam? Okay, so what does this have to do with this discussion about the fault with Alex?
It's just a small step that allows you to figure out the closed form rate of change function out of your accumulation function.
Okay, so you're telling me this is what now? What is this a formula right here?
It's a
Closed form rate of, he's saying that's a closed form rate of change. Closed form rate of change function. What does that have to do with our discussion? What's that?
It's a way so we don't have to zoom in and get a really small change max and change y. That way we can just find the derivative of that, which is the rate of change function.
Okay.
Simulation. Plug in any x value and get an exact rate of change.
He's saying we can plug in any x value now and get an exact rate of change out of this. And we don't have to zoom in on all the points. We don't have to zoom in one at a time and estimate these rates of change by zooming in and finding delta y and delta x. What do you think? Right. Okay, so go ahead and find. So I want you to use this function now to find the exact rate of change at these points. I don't want everyone to do all of them. So just start somewhere in the table. Try to do 2, okay? So you're going to use graphing calculator or use your handheld. Here's the rate of change. Find the value of the exact rate of change at these x values. But don't start at the top and work your way down. Just start anywhere. You're right, but you didn't make the connection to the conversation. Yeah, you're right. So, but what does it have to do with? So it's another version of the function.
Yeah.
It's another version of the function. Let's do it.
Do they compare the mastery exam scores from our curriculum to others?
Loosely.
Loosely?
Yeah, like we'll look at the pass rate on the first attempt.
I was about to say, if there's a correlation between people that take this class and if there's a correlation.
Yeah. Anybody do 0.25? Should have gotten 4.79 for the rate of change, exact rate of change. Okay, so hopefully everyone's done at least one by now. Here's what they are. Did it work? But anyway, so where do these numbers come from? They just come from taking x, the x value, and plugging it into the rate of change formula that we got by doing the derivative rules on the original accumulation function. Okay, so we represented this rate function with a table of values that we got by estimating certain x values. What's the advantage to this? What's the advantage of this over the table that we had before, first and third columns? It's exact, and there's another huge advantage. Faster to calculate values, but what's that? You can go back. Okay. Good, right, so yeah, that's right. How many values of rate of change did we get in our table? 7. How many values of rate of change can we get from that one? Any x value that you want. And boom, it'll spit out the corresponding rate of change. So having the function as a expression, as a defined function with a rule like this.
We don't need the graph.
We don't even need the graph, right? So we can just plug in x it spits out a number, but do you understand what the number means that it spits out, right? So it's just like it. So how are our estimates? How are our estimates compared to the exact values?
Really good.
Pretty good, right? All of them are close in the ballpark.
Oh.
Is there another part to this? Okay, so let's go to GC. So the question is, how can we graph the rate function? Let's start with, if we just had that table of values. So there's the rate function. Oh, sorry, that's the original function. At 0.25, what did we estimate for the rate of change? Or let's do exact. What did we get for the rate of change? At 0.25. 4.79. Something like this. There's a point. So we're building the rate of change function. Okay, what about at 1? Rate of change. Isn't it around 2? 1.84, a little bit lower. Okay? And what was the next one we had? Help me out here. Who made the table? What's the next x value? 3 or 4.1? 3. What was it at 3? Negative 0.96. And then 4.1 was about 0. 0.08. Okay. And then 2.232 at 6. Something like that. And then at 8.67. So what are we doing? Now we're tracking the rate of change of the fault width as time goes by. We're making the rate of change function. So what was it doing? It was increasing quickly at first, then it was increasing more slowly. And then somewhere around here, it was holding constant, around 2, right? And then at 3, it was decreasing, so we have a negative rate of change. And then 4.1, holding constant again. At 6, increasing moderately, so it's about 2 centimeters a month. And then increasing slowly. At 8, it was like 0.67. So this is our rate of change. We could kind of try to sketch it based on our points here. Something like this. This is tracking the rate of change of the width. Now, how can we graph it exactly? We have 2 ways we can graph it exactly. What are the 2 ways that we can graph this thing exactly? Yeah.
Graph the rate of change function.
The formula. Yeah, so the one that we found using the derivative rules, we just graph that. And what's the other way that we could? Is there anything to say? Difference quotient, right? So we can do the difference quotient, and then, so we can graph this, right? If we graph this, and we say that for a very small h. And so, which one do we really trust? I mean, we had to do some algebra. We could make mistakes. This one, we know for sure, is always accurate. So here we go. So for a very small h, I'm going to graph our difference quotient for our function f. See how we did. Okay, so there's the exact. So I'll get rid of mine now. So this is the rate of change of this one as a function. And then here, this was using the rules, using the chain rule and cosine and sine. So I'll do that in black, and it should be right on top of it. And it is. So I'm doing it both by the difference quotient, the open form, and the closed form. Right? So this is the open form version. This is the closed form version. And if you have a very small enough h with the open form version, you get the rate of change. Okay, so that was probably one of the top 3 and most important discussions of the semester. Okay, so this rate of change is what calculus is all about, and understanding what a rate of change function is. What a rate of change function is. Okay, so these ideas will be your quiz for Monday. this discussion. So it's not going to be asking you to replicate everything exactly the way we just did this whole scenario. It's going to be to see if you understand all these ideas, okay, in the quiz Monday. Okay. Any questions? Any questions? I hope this thing about rate of change functions is starting to come together, right? So given any time x, the function outputs the rate of change at that time. When the accumulation is increasing, our rate is positive. When the accumulation is decreasing, our rate is negative. Okay, so all these connections. Anybody have a question? Okay, so let's go ahead and open up your laptop, and there's a file that I posted in reading, what do I call it? Reading some homework on Blackboard. It's a GC file. Go ahead and download that. It looks like this once you get it open. Did you find the file? So you want to download that and open it in GC. And then you should be able to look like this. It should look like this. And what you'll find out is if you put your cursor over, there should be a red dot, a red point. If you put your cursor over it, it kind of turns to like crosshairs, and you can actually drag that point around. And notice what happens to those first 3 command lines when you do that. So it tracks A is the x coordinate of the point. Okay? B is the y coordinate of the point.
How do you get to the red dot?
So hit enter to graph, and it should come up. And then you should be able to drag it around. Are we having success? Okay, again, so as you drag the point around, wherever you leave it, it'll tell you the x-coordinate of the point as A, the y-coordinate as B, and then it'll give the value of this expression, a squared plus b cubed minus 2ab, for the current values of A and B. And if you move, you'll change your coordinates, you'll change A and B, and then that value of the expression will change. So here's you've got that handout that I gave you. Your goal is to plot all the points where, please stick to this set of instructions. Don't go off on a tangent doing something else. Stick to this. Plot all the points where you can find that expression, looking up there in the 3rd line, is equal to 7. Okay, so as you notice, you move it around, you get different values. So let's see if I can find one here. Should be able to, right? Oh, here we go. And then just close is close enough, right? So, come on. There we go. So I found one right here about A equals 4 and B equals, or 3.89 and 1.38, where the value is 7. Okay, so here's the deal. Don't write down the coordinates. It's going to take way too long. Just set it somewhere where you found it's equal to 7, like at this point, and then go to your graph and just roughly sketch that point based on the coordinates that you see on the screen, A and B. Don't try to write down the numbers. It'll just take too long. The goal here is to plot as many points as you can find as quickly as you can find, such that that expression is very close to 7. Does the math make sense? So whatever method you can use to plot as many points as you can find. Our goal is to plot all of them. Try to plot all of them on your white paper. Do you have 2 or 3 points plotted already? Hopefully you do. There are some in all 4 quadrants. There are some in all 4 quadrants.
It's a little bit after 3 on the x-axis, and is it go to?
Uh-oh. Thank you. Anybody get them all yet?
Wait, there's some.
We're gonna have to. We'll want to plot all the points. That's the question. You think you're smart or something?
Huh?
You think you're smart or something?
Sometimes. In this class, not so much. Dude, I'm starting to. Maybe. That's what I was gonna say. He knows where all of them are.
I have an idea. Seen it before.
What? So once we connect them, are we gonna like picture something?
So
Dude, there's some along the way. I knew this reminded me of something.
get them all yet. How many are there? There's a lot, someone said. Yes, there's a lot. More than we could do in class, okay? More than we could do all semester. So what we're really interested in is, start a new command line. We know our A is X, right? And our B is Y. So minus 2xy. And we want that expression to equal 7. Y cubed, thank you. That would have been anticlimactic. Okay, so what happens if I graph this equation where x squared plus y cubed minus 2xy equals 7? It's going to give us all the points. Okay? Remember, when you look at a curve, what are you looking at? You're looking at a bunch of points. This exercise to reinforce that. So which points are these? How would you describe which points are these? So if we take a point like this right here, what can you tell me about this black point right here? It equals 7? No, points don't equal 7. Point is an object. The point is a location. What can you tell me about that point? Right. The coordinates of that point satisfy that equation. Okay? The coordinates will satisfy that equation. What can you tell me about this point? It won't, right? You put in the x and the y coordinates, it won't equal 7. So here's the kind of the point. When we have this equation, hold on a sec. We have this equation, and we say, this is the graph of this equation. It's not that that is like a name or a label for this curve. It's a mathematical the curve is a mathematical representation of that. It's every point whose coordinates x and y make that thing true. If the point's on the curve, that equation is satisfied. If the point is off the curve, that equation won't be satisfied. So when you see a curve, you're seeing every point whose coordinates make that thing true. And that's where we'll pick it up Monday. Let's do cards, please. Let's do cards. Sorry.